All right, we can let folks in.
We're live.
Good morning, everybody. This is Drew Bartlett, Executive Director for the South Florida Water Management District. Well, almost a couple of years ago, the governor challenged DEP and the Water Management District to come up with a water quality component for the C-43 reservoir. And so we all embarked upon this feasibility study to figure out what might work for ensuring we have water quality in and leaving the C-43 reservoir. And a lot of work has been done along these lines. And I really appreciate the Water Management District team and the team from JTech on all the work that they've done to pull this together. I specifically want to thank the working group, Holly Milbrandt from the city of Sanibel, James Evans also, Mike Cook, Lehigh Acres, Maya Robert from Cape Coral, Roland Ottolini from Lee County, Ed Smith from DEP, and Shane Parker from Henry County. I appreciate your perseverance in helping us craft some of these feasibility study recommendations. And I also want to thank the public. We've had a number of routine engagements on this. I truly appreciate the public's engagement and feedback during this process. This is the first step in the process. There are still more steps to be done to figure out what this ultimately looks like and operates. And so I look forward to this team presenting this feasibility study to you. I will be here looking forward to it as well. It's a good report, and I look forward to this workshop. Thank you, Georgia. I am going to turn it over to you to facilitate this meeting.
Thanks, Drew. Hello, everyone, and welcome to our meeting to update you on the C-43 West Basin Storage Reservoir Water Quality Feasibility Study. My name is Georgia Vince, and I'm supporting the South Florida Water Management District on this important project. We are bringing this meeting to you today via Zoom. And we just wanted to quickly run through a couple of the meeting functions. We'll be taking questions using the question and answer feature where you can type in your question and we will either type a response or ask a member of the panel to read and respond to the question. For comments, you can raise your hand during the Q&A sessions and we will call on you to unmute your phone and present your comments. At the end of the presentation, we'll be utilizing another program called Menti to obtain input and feedback from Zoom participants. Menti can be accessed from a separate browser window or from your smartphone, and we'll provide the website address and code when we get to that part of the presentation. For today's meeting, we'll give you a quick refresher of the study goals and objectives and provide you an update on the final feasibility study results and recommendations. The South Florida Water Management District will provide an update on a pilot study that is underway related to the results of the feasibility study and provide details about the next steps planned for the water quality plan for the reservoir. And of course, we'll be taking your questions and comments throughout the presentation and using Menti to obtain your input. The feasibility study was supported by the working group and which includes several municipality entities within the region. The following are our working group members. For the South Florida Water Management District, the lead is Kim Fikowski, the project manager. For the Florida Department of Environmental Protection, the working group representative is Edward Smith, Director of Office Water Policy and Ecosystem Restoration. For Hendry County, Shane Parker is the Public Works Director. For Lee County, Roland Adelini is the Director of Natural Resources. For the City of Cape Coral, Maya Robert is the Environmental Resource Division Manager. For the City of Sanibel, Holly Milbrandt is the Director of Natural Resources. And the Lehigh Acres Municipal Services Improvement District, Michael Cook is the Assistant District Manager. The consultant team leading the study efforts is JTEC, a joint venture between Jacobs Engineering and Tetra Tech. You'll be hearing from the consulting team today during the presentation, including Marcy Frick and Jim Bays, and Chris Keller from Wetlands Solutions, Inc. In case this is your first time attending a meeting regarding the feasibility study, here's some general project background information. In January of 2019, Governor DeSantis signed an executive order to greater the protection of Florida's environment and water quality. It included efforts to reduce harmful algae blooms, and specific to today's topic, it included a directive to study additional water quality treatment opportunities for water leaving the C-43 West Basin Storage Reservoir. The primary objective of the study is to identify opportunities to provide additional treatment and improve water quality leaving the reservoir. During the study, we identified and evaluated treatment technologies that may be implemented with the reservoir project, with the ultimate goal being to identify at least 3 alternatives. The study evaluated pre-treatment opportunities prior to entering the reservoir, in reservoir treatment, post-storage treatment or water leaving the reservoir. We ensured the technology is cost-effective and technically feasible. We evaluated both conventional and innovative treatment technologies. We considered biological, chemical, and physical water quality treatment technologies. And the final alternatives must be scalable and available for long-term operation, and must be compatible with the objectives of the C-43 reservoir project. The working group and consultant team identified constraints for the feasibility study. The identified alternatives cannot affect the congressionally approved C-43 West Basin Storage Reservoir project purposes, benefits, infrastructure, construction schedule, or operation, and the available project lands have not been specifically identified for the study. The C-43 reservoir and the selective treatment components are not intended to achieve the full compliance of the Caloosahatchee River TMDLs for the basin. The project was initiated in July of 2019, and we have had several public meetings as the project has progressed over time. We have incorporated feedback and public input from those meetings throughout the process, and we have finalized the feasibility study and will be presenting our results and next steps to you today. A little history on the C-43 West Basin Storage Reservoir. It's a component of the Comprehensive Everglades Restoration Plan, and the project is funded by annual Florida legislative appropriations, and the U.S. Army Corps of Engineers will credit eligible project costs. The purpose of the reservoir is to capture excess basin runoff and Lake Okeechobee releases to store water to improve the quantity, timing, and distribution of discharges to the Caloosahatchee estuary. Another purpose of the project is to maintain water supply for existing users. The C-43 reservoir is located in Glades County or Hendry County along the C-43 river or canal west of Lake Okeechobee between the Ortona and upstream of the Franklin Locks, just east of the Townsend Canal. This is a 10,500 acre project that will provide above ground storage. Flows from the river will be directed down to the Townsend Canal and into the reservoir. When the river and estuary call for it, water that is stored will be discharged through the Townsend Canal and back into the river and estuary. Marcy Frick will now discuss treatment technologies that were evaluated for the study.
Thanks, Georgia. Our search for appropriate treatment technologies is focused on three primary water quality parameters: nitrogen and phosphorus, which are the nutrients that drive algae growth, and total suspended solids, which includes both algae and organic matter. Nitrogen exists in multiple forms, which vary in their availability to algae, including organic nitrogen and inorganic nitrogen that includes ammonia and nitrate. Phosphorus occurs in dissolved and particulate forms, which have different mechanisms for treatment. And so on the next slide, we looked at different ways on how to treat. For this project, because we face area and operational constraints, we considered the spectrum of natural and conventional treatment systems for pre-treatment, in-reservoir treatment, or post-treatment. Natural systems use the same chemical and biological processes for treatment as conventional systems. Where conventional systems build tank-based treatment reactors of concrete and steel and move water and add compounds using electricity and chemicals, natural treatment systems are typically land-based systems that rely upon gravity flow and natural plant, soil, and microbes to provide the media and biological habitat that sustain these processes at natural rates. As a result, fewer staff are required to operate and less time in the field is needed for maintenance and monitoring processes are reduced significantly and fewer residuals are produced. This often means lower long-term unit operational cost per pound of nutrient removal for natural systems. On the next slide, we prepared an information collection summary report for this project, which was made available on April 3rd. In this report, we summarized the attributes of 38 chemical, physical, and biological technologies. These technologies were from the Florida Department of Environmental Technology Library, working group member experience and case studies, vendor submittals, and public input from past meetings. As part of the information collection summary report, we eliminated 13 technologies from further evaluation that were not applicable to the C-43 West Basin Storage Reservoir and or did not have enough information available. The remaining 25 technologies were carried over for further evaluation in the feasibility study. Both the information collection summary report and feasibility study are posted on the study website, and that link is shown at the bottom of the slide. For our technology evaluation, we evaluated them using key attributes. These attributes included whether Florida case studies were available and whether the data were suitable for analysis, nutrient removal data and to what extent it could be used to scale up to treat large flows associated with the reservoir, the general land requirements and whether its features were compatible with the reservoir system and location, if treatment residuals are produced and how they would be managed, the amount of energy required, the schedule for implementation, operation or O&M requirements, general costs for construction, O&M, and cost benefits, as well as regulatory constraints with the provision that the technology cannot harm the environment. And with that, I'll turn it over to Chris Keller.
Thanks, Marcy. I'm going to go through several of the technologies that were reviewed and then hand it over to Jim Bays, who will cover the rest of them. The first one that I have to talk about this morning is constructed treatment wetlands. And these are large created marshes that are designed to provide natural water quality improvement. They're fairly common throughout South Florida, and you may have heard of them in your communities or in the region referred to as stormwater treatment areas or filter marshes. They reduce nutrient concentrations in the water by consuming nitrogen and phosphorus that fuels the growth of wetland plants. And those nutrients also serve as an energy source for microbes that live in the wetland community that also provide a wide variety of water quality improvement processes. There are many successful applications of this technology in Florida and also around the world. And we're very fortunate to have robust data sets here in Florida that we can use from large scale systems to be able to forecast the performance of a system for the C-43 reservoir. The general removal efficiencies for nutrients range from about 20 to 40% for total nitrogen, 75 to 90% for total phosphorus, and over 90% for suspended algal solids. Treatment wetlands generally require very large land areas, and correspondingly have high capital costs required for land acquisition and construction. They do, however, provide the opportunity to see a lot of savings in terms of operations and maintenance costs above and beyond what you may see with some of the conventional technologies. Most of the annual costs that are associated with operating a treatment wetland or a stormwater treatment area are associated with supplying electricity to operate the pump stations that are needed to route water to and from the wetlands. Treatment wetlands accrete residuals in the form of new sediments, which are made up of decomposing vegetative matter. That accretion rate, however, is very slow, on the order of about 0.5 to 1 centimeter of thickness per year, which generally results in a life expectancy for a treatment wetland system of 30 to 50 years. Treatment wetland for the C-43 reservoir is one of the technologies that could be used either before water is delivered to the reservoir or after water is discharged from the reservoir before it returns back to the C-43. The next technology is sand filtration, which involves the gravity separation of particles such as algae and suspended solids in the water column by forcing the water to drain through a bed of sand or other media. Sand filtration is one of the technologies that we consider to be a passive system or a natural technology, because other than needing energy for pumping, there are no other external energy or chemical inputs required to make these types of systems work. There are a few applications of this technology in Florida. The largest is currently under construction for the phosphate industry in Central Florida. The general removal efficiencies for total nitrogen are similar to those for treatment wetlands at about 20 to 40%. They run at about 25 to 50% reduction in phosphorus concentrations and over 90% for suspended algal solids. Similarly to treatment wetlands, sand filtration generally requires a large land area, therefore likely to have correspondingly large capital costs for land acquisition and construction. Again, because these are a passive system and only rely on electrical costs for pumping, they have generally lower operations and maintenance costs compared to conventional technologies. The primary operation and maintenance activity for these, besides pumping, is the periodic replacement of the upper layers of the sand every 3 to 5 years. As with the treatment wetlands, this is one of the technologies that could be applied before or after the water enters the reservoir. The last one that I'm going to discuss is the hybrid wetlands treatment technology, which combines the physicochemical processes of coagulation with the natural settling and uptake processes that occur in treatment wetlands. In this particular example, a coagulant such as alum, which you'll hear more about in a moment, is dosed to bond with nutrient ions and form particles that then settle out in wetland basins. There are several successful applications of the technology in Florida. Sorry for that delay. The removal efficiencies range from about 50 to 60% for total nitrogen, 80 to 90% for total phosphorus, and over 90% for suspended algal solids. Because they're enhanced or intensified by adding chemicals, they require reduced land area and reduced capital costs when compared to constructed treatment wetlands. The requirement for chemical addition, however, increases their O&M costs in comparison to treatment wetlands. They do generate solids that require periodic removal and disposal. And these hybrid wetlands can be used to treat water either before or after storage in the reservoir. With that, I'll hand it over to Jim to discuss the remaining technologies.
Thanks, Chris. I'll be speaking first about alum treatment, picking up on Chris's connection there. So for coagulant treatment using alum, it's used commonly to coagulate nutrients by particle charge neutralization and solid sedimentation in offline lagoons or within, in this case, the reservoir. This approach has a long and successful history in Florida and is well studied with ample performance data from full-scale facilities such as the Nutrient Reduction Facility in Lake County. Removal rates are typically high in nitrogen in the range of 50 to 70%, and very high for phosphorus in the range of 50 to 90%, with over 90% algal solids removal. The land area requirement is relatively small and consists primarily of settling basins, chemical storage, and solids dewatering and drying facilities. The O&M cost is moderate to high given the continuous need for chemicals and management over time. The removed flock requires dewatering and storage, which is the largest open concern over the long term. Power is required for pumps, dosing, and mixing. The next technology is electrocoagulation. It's the same principle, but a different method of treatment. Electrocoagulation, or EC, as we call it, is the coagulation of nutrients by electrode particle charge neutralization and subsequent solids sedimentation. The system is relatively new to Florida, with limited Florida case studies. The studies have shown that this approach has consistently high removal of nitrogen, phosphorus, and algal solids, up to 90% typically. The system would be relatively compact with a low land area required, but would have a high capital cost and a high O&M cost. One benefit of this approach is a lower residuals production compared to alum treatment, for example, but still generates solids that require disposal. Power requirements are high to operate the system, pumps, and related machinery and the equipment in the system. Okay. Bolden gold is a sorption media developed by the University of Central Florida that uses a mix of sand, tire crumbs, and clay particles to absorb and filter nutrients in engineered basins. There have been over 200 applications in Florida, and performance data indicate potential TN removal ranges of 75 to 90% and total phosphorus removal of 50 to 90%. Media beds are relatively small and require a moderate area. The spent media must be replaced over time. O&M costs are relatively high because of the replacement costs, but other operational needs are minimal. And I think that's it for us on the overall technology review, and we'll take some questions now. Georgia.
Thanks, Jim. So if you have any questions, you can use the Q&A feature of the Zoom meeting now. You can raise your hand in the Zoom meeting to provide a comment regarding the information presented in this section. If you're on the phone and not using the internet, you can hit *9 to raise and lower your hand and *6 to mute or unmute your phone. And you'll also have an opportunity to type in questions at the end of the presentation using the Menti interactive tool.
We did just receive a question, Georgia.
Do you want to read that, Marcia?
Sure. Yes, it says, are there water depth limitations to the alternative treatment technologies?
And I think I'll ask Jim Bays to kick off the response to that question. Are there depth limitations to the alternative treatment technologies?
Yeah, I take that question to speak to how deep, I guess, these media beds might need to be. I think that may be the question. So please clarify if I'm not hearing that correctly. I think the general answer is that these types of media bed treatment will, for example, for the Bolden gold, we'd look at media depths of 3 to 5 feet or so. Right now, we're looking at cumulatively about a 5-foot media depth for filtration, testing a 3-foot depth now, as you'll hear. Hope I got that question right. So
Jim, we did get a clarification. It was the questions about the depth of the overlaying water column.
Okay, for the overlaying water column, The depth for the sand filter, for example, would be on the order of a foot or so, but the water depth over the Bolden Gold facilities could essentially be at grade, or just a few inches, or just enough water to spread the flow over the top of the system for filtration. They're not intended to be very high water depth, not intended to be very deep depths above that system. For the settling ponds for alum treatments, typically we're looking at depths of 9 to 10 feet or so in these areas where they accumulate solids over time. So let me know if I still have that question right, or if that's helpful, since I can't see the question directly here.
Yep, thank you. Another question, have you considered solar energy for the alum facilities?
Right now, we're looking at a direct power from the local power grid to operate the treatment facilities, whether it's alum or any of these others that require treatment. Certainly we'll need power for pumping. To operate by a solar power, we have not looked at that specifically. That could be considered down the road, or integrated into the facility, depending on the area requirements. But the power intensity required to operate the mixers, the dosing machines, and pumps, would have to be looked at, the power requirements to operate that relative to solar. Right now, we're just assuming we'll take power from the grid.
Right, and just to add on to that, Jim, that would be something that would be considered during detailed design of the project. We're currently just in the phase of identifying the technology.
Exactly, that's fairly said. It's a conceptual design, conceptual plan phase here.
Jim, the next question I think is for you as well, is what is the proposed alum dosage concentration?
I think this, I have to look back at our notes on this. I think it's in the order of 10 to 12 milligrams per liter. I'm kind of going from memory there, so hopefully that's helpful. It is being tested now, and Cassandra will have information on this right now at C-43, and that is usually a dose determination that happens in more detailed design.
I wanted to send the next question to Chris Keller. It's a question about sand filtration, and the question is, what is the most ideal water depth for sand filtration?
Again, I think Jim addressed this partially in his response about Bolden Gold as well, and sand filtration basically just needs enough water over the top of the sand to spread that water out laterally across the entire surface, so the water can then soak through the sand media bed. So, a foot, 2 feet would probably be about the greatest water depth that would be required over the actual media bed to operate that type of system.
Mm-hmm. I agree with that.
Okay, I believe we've answered all of the questions that were presented at this time. So we're going to go further into details of the feasibility study, looking at the technologies that we've identified and how they ranked at the end of the additional analysis. And I'm going to turn it back to Chris Keller.
Thank you. So as Marcy mentioned a few slides back, there were a number of attributes that the technologies had to be screened through to even make the list from the very first large list of technologies down to the top 10 or so. And once we had those, we needed to take another more detailed look at those to really see which ones would fit well in the context of the C-43 reservoir project. So while the most obvious ranking attributes would be related to cost and cost effectiveness and total amount of nutrients that could be removed, the working group suggested that the team also include these other attributes that you see on the slide in the ranking methodology. So with their help, we identified these 10 attributes that were then weighted and ranked for each of the top 10 technologies. I won't go through all of them, but their individual weights are shown there. The highest weighted, the most important attributes are those with the weights of 4 and 5. And you see how the weighting diminishes there, reduces as we look at the other factors. So those included, just as a couple of examples, scalability. How much experience is there, particularly in Florida, with technology A at a similar scale to what is required for the C-43 reservoir? Habitat, the first one shown in yellow there. To what extent does the technology provide ancillary benefits to fish and wildlife by providing habitat for them? You can see where something like a sand filter doesn't have habitat value for fish, but a treatment wetland would. And then the lowest level there was the schedule of implementation and the amount of time needed to construct and implement the treatment technology. Next slide. So the top 10 technologies are shown there on the left-hand side, ranging from treatment wetlands down to the Nutrigon media. And those attributes from the prior slide with the same color scheme there are shown across the top of this graphic. And the consulting team with input from the working group developed scores for each technology and for each of these attributes that range from 0 to 2. With 2 generally being the preferred score, the highest score, and 0 being the least. Those scores were then multiplied by the weights to come up with the overall scores that are shown in the second to last column on the right. And we see that treatment wetlands came out with the highest overall score at 54, and then ranked number one, as the first place ranking for these non-cost and non-nutrient removal attributes. Next slide. This slide presents that same information, but in a different form, with the rankings shown at the ends of the blue bars and the attribute composite scores shown by the length of the bar. So that 54 that the treatment wetlands received on the previous slide is there reflected in the length of that bar. And you see how those individual technologies fell out, with treatment wetlands ranking first, Alum Treatment and the hybrid wetland treatment technology tying for second place, leaving sand filtration in 4th and Bolden Gold in 5th. Next slide. So in order to take the next step and begin to evaluate these top 10 technologies and compare them in terms of their ability to provide a necessary level of water quality treatment, the consulting team and working group developed some design objectives based on an analysis of actual historical water quality in the C-43 canal. What the team came up with was objectives to be able, for each of these technologies, to be able to reduce total nitrogen from 1.5 to 1 milligram per liter, total phosphorus from 0.16 to 0.08 milligrams per liter, and total suspended solids from 20 to 10 milligrams per liter. And these improvements in water quality would have to be provided for a flow of 457 cubic feet per second. Next slide. So as I mentioned, each of the technologies was sized then based on those design objectives to achieve those minimum design goals of reducing the TN, for example, from 1.5 to 1 milligram per liter. Total masses at those flows of 457 cubic feet per second were summed over a 20-year planning period. And those were combined with net present value capital and operations and maintenance costs, excluding the acquisition of land and the conveyance infrastructure necessary to deliver water to each of these technologies, to develop these overall cost effectiveness values for total nitrogen, total phosphorus, and total suspended solids. So the attribute ranks from the green, yellow, and red graphic that I showed a few minutes ago is there in the second column, and the cost effectiveness for each of the water quality parameters of interest, total nitrogen, phosphorus, and suspended solids are shown in the next three columns. And then the combined overall ranks, including cost effectiveness and the attribute rankings, are shown on the right-hand side. In this case, we see that alum treatment ranked first, treatment wetlands second, hybrid wetlands third, Bolden gold and sand filtration coming in fourth and fifth, and the rest of the technologies there in 6th through 10th place. Next slide. This is another presentation of that same data from the prior slide, but in this case looking at more of a scatter plot where the attribute ranks, those non-cost, non-nutrient removal attributes, are shown, the score, the composite score for those shown on the x-axis, the bottom scale, and the nitrogen cost effectiveness ranking, nitrogen being the key parameter of interest in the C-43 watershed, shown on the left-hand side. So the take-home message from this slide is that those technologies that fall in that lower left quadrant with low dollar per pound numbers for nitrogen removal and high rankings being the lower scores for those other attributes being the preferred technologies. And again, we see that the wetlands, alum, hybrid wetlands are firmly within that lower left quadrant, and the Bolden gold and sand filtration are right there on the edges. Next slide, please. So with the identification of those top 5 technologies, the team looked to develop a short list of technologies that could then either stand alone or be combined to provide another level of service. So there's 2 ways that those technologies can be combined. One is in series, which is shown there at the top, where the inflow from the watershed or from the reservoir flows through the first technology, and that water then flows through the second technology before being discharged. The second is the parallel configuration, where the inflow water splits, with some of it treated by the first technology and the remainder by the second technology before those outflows are recombined. So a series configuration, the top graphic there, is one where each technology maybe provides treatment for a different parameter. Maybe one is really good for phosphorus, the other better for nitrogen, or when the first technology transforms parameters into a form that is more easily dealt with by the second technology. So there's some kind of benefit there of having these 2 things operating together. And the parallel technologies configuration shown on the bottom there maybe is one where you use one technology for lower flows and bring the second technology online when you need to treat higher flows. Next slide. So as there was a hint of with the discussion of the technologies in series, these really need to be compatible with each other. So what the team did with this graphic here is look at the upstream technology for a series configuration across the top. Those are the names shown in gray boxes. Those technologies being followed by a downstream technology in the blue boxes on the left. And then our assessment, the team's assessment of whether those technologies are compatible with each other and whether there's any reason to pair them up. So what we see here is that the alum treatment going across the top, so towards the middle, where alum is shown in gray, the team felt that alum could be followed by a treatment wetland. or by a hybrid wetland system or by electrocoagulation, but there wasn't any significant benefit in following alum treatment with either sand filtration or Bolden gold. So that's kind of the approach to looking at the data in this chart. Next.
So thanks, Chris. So from the attribute ranking analysis we just showed there, we found that the STA, alum, and hybrid wetlands technologies achieved a balance of nutrient removal effectiveness while meeting desirable characteristics as a technology. However, there were other considerations that we knew were important. For one, is there enough land to meet the STA performance? And is there an opportunity to incorporate other innovative technologies, such as in a parallel or series combination? So this led to the creation of combinations of technologies. For one combination, we proposed a treatment wetland to treat a portion of the flow and a Bolden gold treatment bed to treat the remainder. So that would be a parallel configuration. This combination was sized conceptually as 1,000 acres for an STA, which was thought to fit within the known available area and would treat 20% of the target flow, and 104 acres for a Bolden gold treatment system to treat the remainder. Similarly, we considered a sand filter to replace the treatment wetland, which was estimated to be 200 acres, coupled with 104 acres for Bolden gold treatment. And the intent of these technologies is to really drive to a passive operation, or as much of a passive operation as possible, while still meeting the performance. Finally, though, we did want to include EC into the considerations because of its high removal effectiveness, and it's perhaps the most highly controllable treatment system of all the technologies we've looked at here. Okay, next. This table, well, for the cost-benefit analysis, we looked at we calculated the cost-benefit to estimate the total cost, including a construction cost for the treatment facility and the water conveyance infrastructure, and the annualized O&M costs for a 20-year period. The benefits of the systems would be estimated by their cumulative mass removal of nitrogen, phosphorus, and suspended solids, and then dividing that amount into the total for the 20-year period to look at the long-term cost benefit. Okay, next slide. This table shows the capital cost, annual O&M, and the net present value of the infrastructure cost. Capital costs range from $47.8 million for the hybrid wetlands to $164 million for the EC system. Operational costs showed a different trend, with wetlands and sand filter combinations having the lowest O&M costs in a range of $1 to $2 million to $8.5 million per year for the hybrid wetlands. So that reflects the more passive operation of the wetland concepts and the lower cost associated. We also factored in conveyance infrastructure costs, like I said, where we proposed that pump stations, conveyance channels, and access roads to support the treatment technologies would have 3 levels: small, medium, and large. Capital and O&M costs were summed over a 20-year period and annualized, and net present value costs ranged from $115 million for alum treatment to $218 million for the EC treatment. So these are long-term, 20-year accumulations of cost of the construction, the capital, and the construction includes the treatment system as well as the conveyance infrastructure. Okay, this table shows the 6 alternatives compared by area, flow, and 20-year net present worth unit removal cost. The largest area requirement is for a full-scale STA at 5,000 acres, and the smallest is for alum treatment at 50 acres, with an EC coming in close behind that at 150 acres. The treated flows range from the analysis objective of an average of 457 CFS for the STA, alum, and hybrid wetlands down to 325 CFS for the Bolden Gold alternatives, and the lowest flow at 229 CFS for EC. This difference in flows with technologies is because the technologies show greater removals than we specified. That is, they'll get to, for example, EC, Bolden Gold, they'll get to lower concentrations than we're targeting, given what we know about their performance. So those are greater removals than we specified, and this would treat a commensurately smaller flow, which would then be blended with remaining flows. So we're really treating a side stream here to get to our total target outflow concentrations in our analysis. Okay. So this slide shows the unit cost data for each parameter in 3 graphs, with nitrogen at the top, phosphorus in the middle, and solids at the bottom. Each graph shows the unit cost data ranging from the highest to lowest, from top to bottom. Total nitrogen, the blue bars, range from $17 per pound removed for alum treatment to $33 per pound removed for EC. So total phosphorus, the orange bars, range from $109 per pound removed for alum treatment to $205 per pound removed for EC. Remember, this is the long-term capital and O&M cost over a 20-year period. The total suspended solids, the gray bars, range from 80 cents per pound removed for alum treatment to $1.64 for EC. So clearly the highest unit costs are with the phosphorus removal. The nitrogen ranges are lower than that. Alum treatment consistently showed the lowest unit cost, and these numbers are consistent with other operating systems, with a relatively large difference in unit costs between the other technologies. That is, the alum is, generally speaking, is significantly lower than the other costs. The EC, electrocoagulation, proved to have a consistently higher unit cost over all the other technologies, even though it is a substantially more controllable and the operations can be more specifically defined for that system. Okay, so next slide. So based on this analysis, alum treatment was ranked first, followed by a treatment wetland with Bolden Gold and hybrid wetland treatment technology, and followed by a sand filter with a Bolden Gold treatment bed. This set of alternatives represents technologies with proven track records, such as alum treatment and treatment wetlands, but supplemented with relatively new technologies, such as hybrid wetlands and Bolden Gold. The relatively lower unit cost for alum treatment is consistent with actual performance of full-scale facilities, and a smaller footprint is required. The relatively greater unit cost for the remaining technologies are fairly similar, and land area requirements are considerably greater. So this is our recommended alternatives moving forward here. Okay, Georgia.
Thanks, Jim. We did get a question about alum toxicity in the receiving water body, and I know that we have included some additional information in the feasibility study itself regarding this topic, and we receive this question often, so I wondered if you just wanted to quickly just address that toxicity question.
Yeah, I think the first place, that is a fair question. It's been something that's been consistently raised over years, but the operational history and performance of existing full-scale facilities operating at similar flows or concentration ranges don't show any toxicity impacts, and the concentration and dosage can be managed to prevent that from happening. It is definitely a consideration. The water chemistry of our water to be treated here also minimizes that potential, but it is our intention here in the basis for the plan is that we would not achieve toxic concentrations, and it would be managed to prevent that.
Thanks, Jim. Just to recap, this is the website available with all this study information available. It's the sfwmd.gov with the C-43 water quality study. And we also have the email address where you can reach any of the project team members on the screen. Believe we're going to have another question and answer session. So if anybody else has any more questions regarding the feasibility study, the 4 recommended alternatives, after this, we're going to move on to the pilot study. So this is a question and answer session to specify any questions you have regarding the feasibility study or anything related to that. So if you have any comments, you can raise your hand and we can call on you. We'll give it a minute or two if anybody has any questions. We will again have questions at the end of the presentation. Okay, I'm not seeing any questions come up or hands being raised by the attendees. So I am going to, again, move forward. Oh, here we go. We got one question from, I'll direct this question to Chris Keller, but the question is, in your experience, how long do treatment wetlands effectively remove nutrients? With age, can't they become a nutrient source?
Okay. So with respect to nitrogen, the predominant processes that remove nitrogen in treatment wetlands are microbial, and they're associated with biofilms or communities of microorganisms that grow attached to the wetland bottom and the stems of vegetation. And so those processes will run indefinitely. There is no reason or normal mechanism under which those removal processes wear out or reach some kind of saturation. With respect to phosphorus, the soils in the system, when wetlands are appropriately sited, will have some absorption capacity for phosphorus, which theoretically will reach a maximum point. But phosphorus is also taken up into plant biomass, which then dies, decomposes, gets shredded up by other small organisms that live in the wetland and create new soils. So there's a continual process that removes phosphorus over the long term in wetlands as well. So in our experience, we don't see a breakthrough or a saturation or a life expectancy related to the processes for either nitrogen or phosphorus removal when wetlands are appropriately designed, sited, and constructed. So the lifespan, as I indicated on one of the earlier slides when first talking about the treatment wetlands technology, generally 30 to 50 years, but that's really only as a result of that slow accretion of new solids, new soils in the wetland. But you know, the STAs that the South Florida District has been operating since the early 90s don't really show any signs of their age at this point, and we have no reason to expect anything different in the C-43 basin.
Thanks, Chris. We have another question. Are the new treatment systems going to be within the same footprint of the existing C-43 project, or did the costs assume the acquisition of land to accommodate the treatment systems? And the answer is that we did not evaluate the cost of additional lands, buying additional lands. The district does own land surrounding the C-43 reservoir project area, but the costs did not assume land acquisition. We will be doing additional analysis, which we'll be talking about a little bit later in the presentation. And so we'll give you some additional details then. The next question is, will the alternatives be evaluated for effectiveness at flow levels beyond 457 CFS? Anyone from the team, Jim, Chris?
Oh, yeah. Sure, George. I just wasn't sure when to pipe up. Yeah, right now, I think we're looking at, we say 457, but operationally, we're looking at ranges up to 600 CFS in that range. The flow, ultimately, the flow dictates the size of the system, so it's an important consideration. But we've looked at, we're basing this number here based on long-term flow expectations for the reservoir. There's definitely would be some high flow periods, whether with releases from the reservoir or intake from the river. And the working approach going forward is that we treat the flow within the range of 457 up to 600 CFS out of that, and look at the effect of that. But yeah, to answer the question directly, we're looking at an average of 457, but we have that range go up to 600 CFS.
All right, thanks, Jim. And for electrocoagulation, is the bulk of the cost in equipment or power usage? Jim, do you recall that from the feasibility study?
Yeah, the bulk of the cost really is the equipment. The power is significantly, it's higher than the other, say, other alum treatment, but the equipment itself is pretty substantially expensive. We did speak with the vendor and looked at some other alternatives to look at different units and reduce the number of units, but there's still substantial cost in the capital of building the treatment units to meet these flow requirements.
Thanks. All right, so we're wrapping up the first hour of the meeting, and so I wanted to move on to provide some time for Cassandra Armstrong to present her findings for the water quality alternative treatment technology preliminary results.
Thanks, Georgia. For those of you who don't know me, I work for the South Florida Water Management District. I'm the section administrator for the Water Quality Treatment Technology section. And I've been working out in the area of the reservoir for several years now. Go ahead and go to the next slide, please. Thanks. So I've been working with the JTech team now for several years, and we did a study looking at wetland treatment of nutrient removal, primarily focused on nitrogen. And based on those results, when I saw the results from the feasibility study and the nutrient removal rates that some of the technologies proposed, I started scratching my head and said, I wonder if that would work for Caloosahatchee water as well. Because one thing about the Caloosahatchee's water, specifically the nitrogen chemistry, it's very unique. It's dominated by dissolved organic nitrogen, and much of that dissolved organic nitrogen is not bioavailable. We found from our study that it was about 10 to 15% of that DON could be broken down by microbes in plants. So seeing the removal efficiencies presented for the Bolden Gold technology and for the the alum technology, I wanted to basically do a double check to make sure that those removal rates were accurate for our specific C-43 source water. So that's the purpose of the pilot study. And as I mentioned, I picked the two chemical-based removal potentials, so the Bolden Gold and the alum. And we're going to take a look over a really short time frame to see how well they did at removing nitrogen and phosphorus from the C-43 water. Go ahead. So for the Bolden Gold study, we used 6 of the mesocosm tanks that are out at BOMA, and we filled 2 of those with the Bolden Gold media. 2 of those were filled with sand only, and 2 of them are controls, and I'll explain what the control looks like in just a bit. We then applied a continuous flow of the C-43 surface water to each of the tanks for about 1 month at a flow rate of 0.005 gallons per minute per foot. Now, this is an order of magnitude lower than what the Bolden Gold was using in the feasibility study. They had a 0.05 gallon per minute rate. So we're a little lower flow rate than that, so keep that in mind. And then we took very frequent, almost daily samples to try to capture what the nutrient removal efficiency curve might look like for this technology over the course of the time. We were informed by the makers of Bolden Gold that there is a 90-day efficiency spin-up. So the initial performance of this technology is not likely to be its optimum performance. So also keep that in mind. So what we are looking at here is just the first month to try to see if it's improving with time. And it'll represent what I would call the first flush of the system, like what it does when it's very first installed and implemented. So the other technology that we looked at was alum. What we did is we collected samples from 3 different locations within the watershed, 3 different times, and then sent that to a lab to do a benchtop study, what they call a jar study, where they tried to find out the appropriate dosing rate for the alum. And then once they found what that appropriate dosing rate would be, what the nutrient removal rates were for that dosing. Let's go ahead and go to the next slide. So here's where we took those samples. On the far left, you'll see BOMA, and there's an aerial picture of what those mesocosms look like. We occupied the 6 tanks that are in the foreground of that picture, and those tanks are located at BOMA. We also took one of the alum samples from this location as well. Then we also took the alum from Hilliard Canal, and also from the rim canal near S77. So that water represented what would be lake water, whereas the Hilliard and the BOMA sites represent Hilliard represented the watershed, and then BOMA theoretically would have represented the mix of the 2, lake and watershed. However, over the course of our 1-month time period, there were no lake releases at that time. So the BOMA site also represents what the watershed of water component looks like. Go ahead and go to the next slide. So this is the construction of the Bolden Gold tanks. Each of the 6 tanks was filled with red river rock to a depth of about a foot. And then it was covered with what was called geofabric, and this was primarily to keep any of the sand and Bolden Gold material from above from getting down into in between the different rock layer. And the rocks were there just kind of as a capture point for the water that would be seeping down from the top down through the media to the bottom. And to collect that water, we constructed 2 stilling mills. You can see in the middle top picture towards the back. They're down in the rock, and there's holes in the bottom, so the water that would be in the rock would also go into that well, and then we siphon the water out to see what the water quality looks like. So for our control, this is where we stopped construction. It's just the red river rock and the geofabric on the bottom, and then we put the water into there, and that's our control. For the sand mesocosms, we put in 3 feet of sand on top of that geofabric, tamped it down so that it was a nice tight density and consistency and consistent across the whole tank. For the Bolden gold, it was 2 feet of Bolden gold material and then capped with 1 foot of sand. And the sand and the Bolden gold were obtained from the same place, so it was all the same material throughout. So go ahead and go to the next slide. For the alum study, we sent our water up to a laboratory where they conducted what are called jar studies. And this is a picture of their setup in their lab. They had multiple cubitaners where they would put in different levels of alum dosing to try to identify what the best dose was for that system, based on how much flak was formed and how clear the water got. For each of the 3 sites, it turned out that the appropriate alum dosing was between 10 and 14 milligrams aluminum per liter, so that was consistent across the 3 different sites. So once they identified what that dosing rate was, they then took that water and analyzed it for the nutrients that were removed from that system. One thing to know also is the alkalinity of the water is very important. You need to have enough alkalinity in the water in order to accommodate the alum dosing, because the alum dosing will actually lower the pH. Fortunately, the C-43 water was found to have adequate alkalinity to buffer the alum dosing. So also, just as a point, go ahead and go to the next slide. So now we're going to get into the data. These first couple of slides are going to be from our Bolden gold experiment. All of the diagrams are set up the same way. Control is blue, sand is orange, and Bolden gold is gray. We're looking at the, over time, days of flow. So we had about 21 days where we actually were able to collect samples. And the y-axis is the reduction of concentration from the inflow concentration. So the 0 line would be the same went in as went out. Anything that is above the 0 line is a reduction in concentration, and anything that's below the 0 line is an actual increase in concentration. So for total organic carbon, our starting concentration range between 20 and 23 milligrams per liter. And as you can see, both the sand and the Bolden gold actually increased that concentration over 40% for Bolden gold. And then that's about day 7 was the lowest. And then it started to increase, meaning that the concentrations were declining, although they stayed higher than what the initial concentration was, whereas the control actually got up to around a 10% removal rate of the total organic carbon. So that was a very interesting find. And remember, this is a first flush type of situation, so it could be very well be that this material is just, we're pulling the material out of the sand that was initially in there. That's likely what has happened. One of the things I would like to draw your attention to is the gap of data between day 15 and day 20. We had a power loss between day 17 and day 20 due to some work that was going out at the site, and so flow had stopped during that period. So there was an interruption in flow. We then got it back going, and then we took our final sample on day 21. So just, that will become important later on, but just to let you know, we did have a disruption in flow, and it was unintended right towards the very end of the project. Okay, go ahead and go to the next slide. So for nitrogen, each one of the treatments was able to remove nitrogen between, let's see, 10 and 40%. The Bolden Gold tended to do better than the other two treatments, but as you can see, the error bars on that data are pretty wide. I didn't run any statistical analysis on any of these treatments, but I would venture to guess that that's probably not a significant difference between Bolden Gold and the sand and the control in their removal rates. You also, again, notice for the sand, there was a very large drop-off of performance at day 21, whereas actually nitrogen was produced 10% greater than the initial concentration. And that, again, was after that flow disruption. So that still something to keep in mind. Could go to the next slide. So dissolved organic nitrogen was the one that I was most interested in because it's the dominant component and it's also very recalcitrant and it's hard to break down. So I was really interested to see how these technologies would work on dissolved organic nitrogen. And as you can see, there was a lot of jumping around the zero line, the initial concentration, but they were all performed very similarly. With sand kind of peaking out at about day 13 with the 30% removal. But generally they started near zero and they ended near zero. So that was definitely not impressive. Go ahead, go to the next slide. Nitrate was where Bolden Gold really shined. As you can see from basically the start of the experiment through to the end, it was almost 100% removal of the initial nitrate concentration. And it stayed that way, with little variability towards the middle, but very impressive removal of nitrate. The control also surprisingly did well, a little bit above the 50% line. But the sand did not do as well. It was definitely less than 50% the majority of the time. And then after that flow disruption, we actually had a very large increase, a doubling in concentration of the nitrate in the system after the flow disruption. Go ahead and go to the next slide. Ammonia, we did not have any ammonia coming into the system initially, so detection level was below, our levels were below detection, so essentially zero from the start. For the control, it stayed that way. Ammonia was not produced during that time, so that's good. The sand also basically stayed at zero, which is what you expect, until after that flow disruption. And then there was an increase of ammonium up to 0.07 milligrams per liter in that last sampling event. And the Bolden Gold actually did produce some ammonia from the initial. It then went to zero between day 10 and day 15, but then again, after that flow disruption, ammonia was produced again to 0.044 milligrams per liter. Go ahead and go to the next slide. So for phosphorus, we started off with a wide range of concentrations, 134 to 204 micrograms per liter. The Bolden Gold did not do very well initially, but then started to increase towards the middle of between day 10 and day 15. But again, after that flow disruption, we were back down to about zero for phosphorus removal. The sand started off really well with close to 60% removal and then declined through time. And then after that flow disruption, we had a lot of production of phosphorus. And then the control actually removed phosphorus the entire time, ranging between 20 and 60%, and with a slight upward trajectory. So that was a very interesting find, given that you would expect that the control wouldn't be very effective at removing phosphorus. It was just red rock and paper. So go ahead and go to the next slide. And for particulate phosphorus, we actually had a little bit of signal. We didn't have enough chemical signal to detect it in the carbon and the nitrogen. But for phosphorus, we did. So this is our test for the particulate removal. And as you can see, the Bolden gold and the sand actually produced quite a bit of particulate phosphorus over the course of the experiment, whereas the control was actually able to remove approximately 50% of the particulate phosphorus in the system. Go to the next slide, please. And lastly, the soluble reactive phosphorus. We actually had removal of that from all of the different treatments. Sand doing the best, having the best performance primarily over the course of the experiment, and Bolden gold having a lot of variability up and down between 20 and 80% removal, and the control slowly increasing its phosphate removal over time. Go ahead and go to the next slide. So these are the results for the alum dosing. It's a lot of data here, but the one thing that I would like for you to focus on is the actual columns, so TOC, TN, TP, because there was very little difference between the sites. All of the sites generally had about the same amount of nutrient removal regardless of day, regardless of site. So primarily just focus on the columns because that's where the important information is. So for total organic carbon, we had between 48 and 72% of the TOC was removed with alum. For nitrogen, total nitrogen, the range was 31 to 61%, which is pretty impressive and in the range that was presented in the feasibility study. Particulate nitrogen, we didn't really have a lot of signal for that except for three times, and that ranged between 65 and 89% of particulate nitrogen removal. And then DON, the chemical I was most concerned about, we actually had quite an impressive removal rate, between 43 and 72% of the DON was removed. This is much higher than a biological system can do. So that was very impressive. The nitrate actually had a little bit of increase in concentration, so it was not removed, it was produced. That's why the negative numbers. It wasn't that high, but there was an increase in nitrate. And ammonia kind of did the same thing. There was an increase in concentration for those two parameters. And for all of the phosphate parameters, we're mostly in the 90s, close to 100% removal for all of the different phosphorus species. So the alum was very effective at removing the nutrients of concern. Go ahead and go to the next slide. So conclusions from this really quick 1-month pilot study. Bolden Gold did a fantastic job removing nitrate. It was close to 100% for the duration of the study. Total nitrogen removal was slightly higher than the control in the sand, averaging about 30%. There was no effective removal of dissolved organic nitrogen. There was an increase in the total organic carbon, ammonia, and particulate phosphorus, and it may be very sensitive to flow disruptions. That was one of the things that the vendor mentioned when we were constructing these, is he wanted to make sure that we were going to have continuous flow, which originally we were supposed to. So evidently this is a known issue for them, is they need to have continuous flow for this technology to work efficiently. And as I mentioned, we are not within their 90-day window of optimum performance. We're only in that first 21 days, 30 days. So this is not what, the data that present here does not reflect what they would have put together for the feasibility study. Go ahead to the next slide. For the alum dosing, It was very effective at removing both carbon, nitrogen, and phosphorus from the different source waters. It had a very high effective removal rate of averaging 54% for dissolved organic nitrogen. There was some increase in the ammonia and nitrate concentration, and the alkalinity was sufficient in order to buffer the pH. However, the lake water had less capacity. They recommended that dosing not go above the 12 milligrams of aluminum per liter. After that, the pH started to fall below 5. And so something to consider when looking at the operation of the reservoir is the timing of when the treatment will be applied, because if we're pulling water out of the C-43 that is dominated by lake water, that may affect the amount of dosing that can be done to that water, as opposed to if it's coming off of primarily from the watershed. So it's something to keep in mind for an operational perspective. Go ahead and go to the next slide. And so fortunately, we were able to secure some additional funds, and we're going to run this project through September of next year so we can get a full year of data instead of just the 1 month. And this will allow us to capture that 90-day optimum nutrient removal. So we'll be able to see what this technology is supposed to look like when it's performing at its optimum. We're in the process of collecting biweekly samples. In fact, they're out there right now getting this week's samples. And this will also allow us to look at the differences between dry season performance and wet season performance, as well as when we have changes in temperature, storm frequencies, lake releases, those types of things. One of the things that I was really interested in doing was taking a look at the effect of the tire crumb, because one of the things that we did notice when we were out there collecting sample is that the smell of the water coming from the Bolden Gold tanks smelled different. It had like a hydrocarbon type of smell to it. So I've added in some, we're going to collect for total PAHs, which is a common chemical that runs off of tire crumb, and we're also adding in some heavy metals that are also very common runoff from tire crumb, so we can get an effect, see what effect that tire crumb is going to have on the water quality from a heavy metal and a hydrocarbon perspective. We're also going to do a sub-study to see if we can ramp that flow up to the same flow that the Bolden Gold vendors recommended, which is 0.05 gallons per minute per foot. We're going to do this for 1 month with weekly sampling. However, due to plumbing constraints out at the site, we're probably going to have to go down to just 1 tank receiving all of the flow instead of it being dispersed between 6 tanks. So we're going to have to do some plumbing and some engineering to get us up to that rate. That's why it's only going to last for 1 month. But we will be doing weekly sampling, so hopefully we'll be able to capture what that system will look like at the higher rate. And then lastly, we're going to redo the aluminum jar study test. Originally, we were using aluminum sulfate. We're going to also do an aluminum chlorohydrate to see if the 2 different types of alum behave differently in their ability to remove nitrogen. And doing this second one will also allow us to take a look at the difference between dry season and wet season. And I think that's my last slide. Yeah. Are there any questions for me?
We do have a couple questions that have come in. So the first question is, what micron size is the geofabric?
Oh, that's a really good question that I do not have an answer to. It is very porous, but you know, water can move through it freely, but sand cannot. So whatever that is, I will have to check that out. I'm not sure the answer to that one.
No problem. So the next question is, given that the pilot study was only performed for 30 days, would you consider the results for the Bolden Gold and Sand study inconclusive thus far? If not, is it your opinion that the performance reported by the vendor isn't as effective as stated?
Right. So yeah, this is definitely just a first flush of what the technology might look like right after it's installed. And we need to continue to do it to get past that 90-day point where they say that optimum performance is actually reached. So yeah, we're going to continue on. Right now, the information that we've gotten is not conclusive and does not represent what was put together for the feasibility study.
All right, thank you. One more question. Would hydraulic residence time be a better metric than flow rate for evaluating performance?
It's possible. Yeah, I would have to give that some thought as to if that would be a better metric to look at. It's possible.
Georgia, that's all we have right now.
RC, this is Chris. I can go ahead and jump in on the end of Cassandra's response there, that the flow rate that she referenced earlier and its comparison to the flow rate that was used in the feasibility study are really hydraulic loading rates. They're essentially the same thing, because in terms of the flow rate, she had gallons per minute per square foot of surface area. So that effectively is a hydraulic loading rate that's being tested.
Thanks, Chris.
Sure.
All right, Cassandra, we got a couple more questions for you. Have you considered pilot testing for polyaluminum chloride as well?
That was not on my list. I'd be very interested I'm not familiar with that chemical, so I'd be interested to learn more about it and see if I need to add it to the list.
Yeah, the chemical and the media that you were testing were specifically identified in the feasibility study. So, you know, that I'm sure prompted your pilot.
Right.
And then were there problems with the fabric clogging is another question.
No, actually, I've been very surprised with how quickly the water moves through that system, and we turned the flow rate on, and within a day we had pretty healthy flow coming out of our out of the tank. So yeah, it has not been a problem so far. Granted, this has only been up to a month. We're still out there. We haven't seen any evidence of any clogging up to this point. So we've been running now. We started in September. We're now into December, so we're 3 months. So yeah, so far so good. No clogging.
All right. Well, I think what we'll do now is move over to the Menti questions. So I'm going to stop sharing my screen.
Georgia, were you going to do the next steps?
Oh, sorry about that. Let me get there, Kim. All right, Kim, you're up.
All right. Hi, I'm Kim Fikowski. I'm the district project manager for this project, and we'll be kicking off the next phase of the project, which is going to be called the C-43 Reservoir Water Quality Component Siting Evaluation in mid-December. The objective is to select one water quality component plan for the C-43 reservoir from the 4 treatment alternatives identified in the feasibility study. And based on stakeholder input, we'll also evaluate the potential for a full-scale STA. Our consultant team, JTech, the local governmental working group, and district staff will evaluate land availability and project location, water conveyance, routing, and infrastructure needs, further water quality analysis of project performance, and then develop detailed conceptual plans and corresponding cost estimates for each of those conceptual plans, that information will be utilized to find the final water quality component plan that we'll select for future design. Next slide. As always, public meetings will be held to keep everyone informed. The meetings will be after the draft siting evaluation report and after the water quality component plan selection. The siting evaluation will be completed in 9 months, and if funded, the selected water quality component plan will move forward to detailed design under a separate contract. The overall goal is to have construction completed and online concurrently with the full operation of the C-43 reservoir. I wanted to thank our JTEC WSI consultants, the local governmental working group, and our district staff for their dedication on this feasibility study, and I look forward to working with all of them in the next phase. I also wanted to thank the public for the studies you've submitted and the excellent questions and comments that you've provided during these public meetings. You've stimulated our team's meeting discussions, and you've enhanced our teamwork product. I'll now turn it back over to Georgia for the Menti portion, where you can continue to provide us with your questions and comments for our this phase as well as the next.
Thanks, Kim. So here are the instructions for the Menti session. If you open a new internet browser on your computer or use your smartphone, you can go to the website menti.com. And when you get to the screen here on your left-hand side, you can enter the code for today, 6915835. And you'll be able to answer the questions that I'll be reading to you through the meeting in the Menti application, and all the answers will be displayed on the screen. So please go to menti.com now, and I will transfer over to that application. All right, hopefully y'all can see my screen.
Looks good, Georgia.
Thank you. So again, at menti.com, use the code 6915835. And the first question is, have you reviewed any of the C-43 reservoir water quality feasibility study documents? And so this is kind of a warm-up question, yes or no, and to see how many, give you all some time to get into menti.com and log in with the code. So the good news is a lot of you have looked at our study documents. As Kim mentioned, we've had a lot of comments, questions, and input from the public, so we certainly appreciate that. I'll give it a few more seconds for people to get logged in and provide your response. All right, so the next question is, list 1 or 2 words that immediately come to mind when you think of the water quality treatment for the C-43 reservoir. Nobody has any words. Absolutely necessary, harmful algae blooms, essential, clean, natural treatment. improved water quality. Innovative. All right. I'm going to move on to the next question. Do you agree with the selected alternatives moving into the siting evaluation? And you can select agree, somewhat agree, disagree. Okay, great. And just as a reminder, all of these results will be saved and posted to the project website after the meeting, so you can review our results. For the next question, which attributes are most important when further analyzing the alternatives? Multiple attributes can be selected. So we have land and construction costs, operation and maintenance requirements, and that includes handling of residuals, nutrient removal efficiency, operational flexibility, habitat creation, and ecosystem benefits. And as you can see, as the answers come in, the numbers are shown there at the top of which attributes are getting the most votes. So it looks like cost and nutrient removal are in the lead here. All right, so for the next question, please type in any questions you have related to the technologies that were evaluated for the study. And we will take questions and provide responses today. And we will also, if any questions are typed in that we don't have the opportunity to respond to today, we will provide responses to in writing on the website. I'll give you a couple minutes to type up your questions. Chris Keller, I'm going to ask you to respond with, will the recommended treatment methods remove humic compounds and clarify the water?
It depends on which one they are or which one is ultimately selected. Some of them would do a better job than others in terms of perhaps making a change in water color. If the water clarity is more driven by the presence of suspended solids or algal particles, then all the technologies that are still under consideration would do a good job of doing that, or they wouldn't have made it this far through the process.
I'll echo that. I agree with that.
Thanks. The next question is how will the use of Bolden gold be affected by intermittent flows in or out of the reservoir? Is this still a viable solution for this application?
Let me take that one there. It's okay.
Thanks.
I think the short answer is that we do expect some dynamic flow coming in and out of the coming from the reservoir to this system, and so that's an important consideration. I'll say that the bulk of the applications out there now for Bolden gold in the field are stormwater related. So its typical application is for systems that are dynamic. I think that one of the take-homes from the early pilot study results here are that there is a process where the system has to become established, and then that performance can and should stabilize from there, given that there's a significant biological component to what's happening in the media beds. So I think that one aspect of it also have to consider is the equalization provided by the reservoir for flows coming out. There's some control over how much water can be discharged, even though it will be variable from day to day. And the intent here is that the sand filter concept, or that the Bolden gold concept that we're looking at here, is either complementary to or parallel to a wetland or a sand filter. We're not really looking at the Bolden gold by itself. So there's inherently some balancing of water flow in either of those two systems, the sand filter or the STA approach. So I think it's, at this stage, it's just one of those operational considerations that we want to look at as we go into the next phase and do this final analysis. It's a good question.
There's a question, is there a plan to provide continuous routine water quality monitoring of the final alternatives to verify the criteria are being met? And I believe that you're talking about the final project that is designed, built in, and put into place. And I believe the answer is yes, water quality monitoring will be a part of any project that's implemented at the reservoir site. There's a question, why is cost not in the same ranking table with the other factors? It seems more weighted than the other things. And as we went through the process, we first pared down the list of technologies by using the attributes, and then we went strictly to a cost benefit analysis of the cost of the project versus the benefits of the nutrient removal. I don't know if Jim, Chris, or Marcy wants to add on to that at all.
I think that we did get some feedback during the course of the study as to not let cost be the sole discriminator of technologies. And so this was the basis for the attribute weighting and ranking that we've used. And so those don't really have cost in there. They're more based upon their other other performance or other features of the technology. So so we tried to look at performance, these other operational requirements, size related issues, scalability, before we and not solely focus on the cost. We could have done that right from the start potentially, and it was always intended to. But the final breakdown here is looking at those technologies that really are that do have they do meet the basic requirements or expectations, and then we use cost as a additional factor beyond that. Georgia, I see a question here about Bolden Gold. Who brought it up? The short answer for that is that it was in the original list of technologies on the DEP's innovative and or approved water quality technologies. Just
Yes.
it's well substantiated.
Yeah, we use the DEP database as a source for identifying technologies as well as other experiences of experts and input from the public. All right, I'm going to move on to the next question. Please type in any questions you have related to the C-43 West Basin Storage Reservoir project. I know we've discussed the reservoir a lot and it's currently under construction with the construction scheduled for December of 2023. Everybody must be up to speed on that project. So seeing none, I'll move on to the next. Whoops. Please type in any additional questions you have about the study or the upcoming siting evaluation and the next steps. Okay, let's move on to the final polling question we have here for today. How would you like to receive communication about the future project updates? I will check the project website. I will track social media, Facebook and Twitter, continue public meetings to provide public project updates, and I regularly check the South Florida Water Management District meeting calendar. All right, looks like public meetings is winning in this poll. And I will leave the screen up and just wrap up the presentation today. I thank everyone for your participation in the meeting, your great questions and feedback on the project study. And we look forward to hearing more from you as we progress to the next steps of the study. I'll leave that up to the district if anyone else wants to provide any closing remarks today. All right, hearing none, thank you again for your participation, and we look forward to providing additional updates in the future about the next steps of the project.